Hello, this is 637. I'm Charles Bouman, and I hope you've recovered from the exam. We can't talk about it yet because not everybody's actually taken it yet, but soon. So today we started random processes. We were talking about power spectra, and in the lab you actually computed the power spectrum of an image. Okay, is an image a random process? No. An image is just an image, right? So, but you can model an image as a random process. And when you do that, you can use that model to try to estimate the power spectrum if it were a random process, right? So, when you compute the power spectrum of something, there's two limiting processes that occur. If you look at this this notes here, the power spectrum of the random process is what you get if you take the expected value of the energy of a truncated portion of the random process and then normalize it by the size of the window and take the limit as n goes to infinity. So you need to truncate it because if you took the Fourier transform of the infinite sequence, then its Fourier transform would be infinite. So in order to get a finite transform, you have to take a truncated piece of it. But when you truncate it, now you're not going to get a perfect estimate of the power spectrum because whenever you truncate something in time, right, what happens is that you spread it in frequency. So the more truncated it is in time, the more spread it is in frequency, right? So in order to be able to, in order to get very fine resolution. In order to get very fine resolution detail in the frequency estimate, you need to use a large window. The size of the resolution and frequency is going to be inversely proportional to the window. So if you have, so this is the random process, right? And you window it to some window like this, okay? So you take this part of it. Okay, that's the random process, and it's truncated to that size window. And the window here is of length n, right? So then the Fourier transform, nominally, roughly speaking, you take 2 pi over n, and that's going to be equal to delta f. That's the sort of the resolution and frequency you have. Now, delta f is in units of radians. If there's a sampling frequency involved, if you sampled the signal at f sub s, right, then delta f, the resolution would be equal to 2 pi over n times f of s. Okay, hold on. So that would be actually this is delta omega. So this would be, let me redo this. This is going to be f sub s over n. So if it was like, I don't know, let's say you were sampling let's say you had a speech signal. Speech is, say, nominally has a bandwidth of 3 kilohertz. Okay? So if the bandwidth of speech is 3 kilohertz, what's the sampling rate you have to use? So that implies that the sampling frequency f sub s has to equal 6 kilohertz, okay? Because you have to sample at least twice the highest frequency. And then, so if you want to have a resolution of, say, I don't know, let's make up something, 1 hertz, okay? That would be very high resolution, okay? But let's say you need 1 hertz resolution. So if delta f, so delta f equals 1, right? 1 hertz. Okay. So that would mean that f sub s over n has to equal that, and f sub s here is going to be 6,000, right? Divided by n, right? So n here has got to be equal to 6,000. This is 6,000 hertz. So the hertz cancel out, and n is equal to 6,000. Right? You solve this equation. You get 1 equals 6,000 over n, so n has to equal 6,000. So n is equal to 6,000, so it's got to be greater than or equal to 6,000 in order to get that much resolution. So a larger window gives you more resolution and frequency. And if you're trying to get a perfect estimate of the power spectrum, no window is large enough. So you have to take the limit as the window goes to infinity. So what it means is that you truncate the signal to some n, but no n is large enough. So whatever you truncate it to, you're going to get some reduction in resolution. And the resolution you'll get in frequency is proportional to the sampling frequency over n, if you're thinking of it as a continuous time signal that's been sampled, or it's equal to 2 pi over n if you're thinking of it as frequencies that go from minus pi to pi. Nominally. I mean, it's not... that's in sort of a nominal level of resolution, within a constant. So then you take the expectation to get the average out the variations in the signal, and then you divide by n to calculate the energy per sample, so that's the power, and you take the limit as n goes to infinity. So this is the power spectrum, okay? Now, in the lab, you actually computed a power spectrum kind of manually, by actually averaging. You took the image, you broke it into blocks. For each block, you computed the Fourier transform, and you took the magnitude of the Fourier transform squared, and that's the energy. You divided that magnitude squared by n, the number of samples, so you got the energy per unit sample. That's the power, and then you average them over the blocks. That's like approximating the expectation. Now the problem is how many blocks do you pick? Well, it's a conundrum, okay? Because if you have usually what happens in one of these applications, you have a fixed amount of data. And now you have to figure out how you're going to use that data to estimate the power spectrum. If you use a lot of blocks, then what's the disadvantage? If you use a lot of blocks, the blocks have to become small, right? So if you use a lot of small blocks, what's the disadvantage? The resolution in the frequency is not going to be high, okay? Because the resolution, as I just pointed out, is related to 1 over n, okay? So if n's small, you won't get so much resolution, okay? So you'll have a smooth estimate in frequency, but the estimate, what's the advantage of making lots of blocks?
Low competition.
Well, that's one advantage, but what's ignoring computation, just in terms of quality? So small blocks have a disadvantage that they give you a smoother estimate in frequency. I mean, the estimate doesn't have as much resolution in frequency, right? But they have an advantage too. They're more you've averaged over a larger number of samples, so that the expectation is less noisy. So there's less variance in your estimate. One of the really fundamental things that comes up in signal processing and estimation is the so-called Biasvariance tradeoff, okay? And this is a classic example, okay? You have two sources of error in your spectral estimate. One is the variance due to noise, okay? The other is the bias due to smoothing, okay? One is a systematic error. The other one's, is an unbiased error, right? That it like causes variations, but the variations don't have sort of a particular bias to them, right? So it's often the case that those things can be traded off. You can go for a low bias estimate that has a lot of variance, or you can go for a low variance estimation that has a lot of bias. Okay. So the so-called Biasvariance trade-off. Okay, so if you make small blocks, the variance will be low, but the bias will be high because it'll be smooth. If you make large blocks, what will happen? In that case, the bias. If you make large blocks, the variance will be low. The bias will be low, but the variance will be high. Okay, so small blocks. You guys actually did this in your lab, right? So small blocks is low variance, and high bias. This is smooth. Smoothing represents bias because it's a systematic change in your estimate. Right? And then large blocks, this is high variance, and this is low bias. This is finer resolution. Okay. By using a large window, you get finer resolution in frequency. Large in time means small in frequency, okay? Any questions about this? And you actually saw the outcome of this in your lab, right? Because when you use one large block, the variance was very high. It was very noisy, your estimate. When you use smaller blocks, it wasn't as noisy. If you recall, it kind of looked like this, okay? The power spectrum was supposed to look like this. You could calculate the exact power spectrum theoretically for the random process you had actually produced in MATLAB, right? So you knew exactly what its power spectrum was supposed to be. Oh no, you didn't. What am I talking about? You actually did it with an action image, right? Okay, but in any case, if you have if you lose a lot of small windows, then it'll be smooth, but it'll be biased. Okay, so it looked like this. Well, maybe it wouldn't look exactly. See, you lose that peak because you don't have the sharp, fine detail. Because this would be the case of small blocks. Okay. The alternative. Let's see if we can get another color going here. I don't know if this will actually come through or not. The alternative is that you use large blocks. Okay, but you only have a few of them. In that case, it may track it quite accurately. But the problem is it'll be very noisy. Well, that's my really bad drawing, okay? But imagine that you saw it. It was very noisy. There was a lot of variation, but it tracks it more accurately. So this would be large block. Okay? Yeah.
Why if I have fine frequencies, I cannot get the peak?
Well, no. If you have fine frequencies, you can get closer to the peak, but you'll never get the peak perfectly, right?
Right. But if I have more frequencies, then it's going to be smoother.
I'm sorry, could you say that?
If I have more frequencies,
yeah,
it seems that it's going to be smoother.
If you have more frequencies, it seems like it should be less noisy, you mean?
Yes.
Okay. No, that's a very good point. It's counterintuitive. It's very counterintuitive. And that's why I have you do the lab. I mean, I try to pick topics for the labs which cut at the heart of some very core issues, right? And I have you do that lab because, to me at least, the first time I ever saw that, I was surprised, okay? It feels like if you make a bigger and bigger window, you should be able to reduce the amount of variation, right? But it doesn't work that way. Because, okay, one way of thinking of it is if you have more frequencies, you're letting through more noise. I don't know if that helps. I mean, part of the answer to your question is this, okay? And I don't mean this to be... I mean it exactly for what it states. I don't mean it to be snippy or something, okay? Is it simply true because it is, okay? I mean, in other words, you derive the equation and that's what it comes out to, okay? But somehow that's not satisfying. I mean, you want to have some insight into why it's true, okay? So one answer to your question is just correct, okay? But the insight is harder for me to give you because every person's different in how they find a result satisfying. Okay, so I'll try, but I'll probably be deficient, and I apologize for that in advance. Okay, but one way of thinking about it is you're letting through more frequencies, and the higher frequencies have a lot of this variation. Okay, another way of thinking about it is that we're averaging less things. See, every power spectrum estimate, whenever we get one of these, when we take the Fourier transform of this random process, okay, before we take the expectation, if we just take the Fourier transform here and we take the square of this, okay, so if you take this thing and we square it, and we divide this by 1 over n, okay, we just take that quantity. It turns out, perhaps surprisingly, that the mean and the variance of every value of y for a particular omega is the mean and standard deviation. The mean and standard deviation have pretty much a fixed ratio. As n goes to infinity, the standard deviation of this thing doesn't go down. Let's see if I can prove that real quickly. Well, I'm a little afraid to do it right now because if I might get into a calculation and it'll take me a while, and then I'll end up making a mistake and it'll be just confusing. Okay, but the standard deviation of this thing does not decrease as n goes down, and that's why if you take if you just take this Fourier transform and look at the spectrum, as n gets smaller and smaller, as n gets larger, what'll happen is this. You would expect that as n gets, so this is 0 and this is, say, pi, okay? You would think that as n gets larger, the thing would become smoother, but it doesn't. What ends up happening is that, so let's say that this is what the theoretical power spectrum should be, right? What it really does is that as you take more samples, the variance stays the same. What ends up happening is that as you get a larger window, it gets more and more fine-grained, but the variance doesn't go down. It's a little bit like in undergraduate electrical engineering, you learn about Gibbs phenomena, okay, where when you have a square wave, okay, that if you have a sharp cutoff, what happens is you go like this. And this overshoot has a fixed percentage of the value of the signal. I forget what it is. It's like 33% or 36% or something like that. And no matter how high the cutoff is, that 36% stays the same. All that happens is this thing gets smaller. So it converges in L2 norm, but it doesn't converge in L infinity norm. And it's the same concept here, that the amount of variation stays constant, but what just changes is the variation gets finer grained. So one way of solving the problem is to smooth this. But if you smooth this, that's actually equivalent to, so filtering this in the frequency is equivalent to multiplying in space, okay? And you've squared this thing. I don't want to get off into too much of a tangent. You've squared this, so that corresponds to taking the autocorrelation in time. So if you smooth this in frequency, it corresponds to taking the autocorrelation function, say, which would be like, you see, the autocorrelation function should be a symmetric function, but it would keep going like this all the way out and windowing it to a finite window. So you throw out all this extra noise and you get a smoother version, okay? But the problem is there's a lot of noise here, but there's some signal too. And you've thrown that away, and that's why you get a biased estimate. It's a pretty fundamental result because you'll see, in fact, we'll talk about this some more, in all kinds of applications, this Biasvariance tradeoff becomes very important, okay? One of the very important examples of that is what we'll talk about later, which is training. Okay, so hopefully I gave you some kind of useful response. Okay, the next thing I want to talk about is random processes. So a stationary random process we talked about before is one in which the statistics are not a function of time, okay? So in second-order stationary random process is a second-order random process whose mean and variance are not a function of time. So if you can take, say, a random process x of mn and say that it's a stationary second-order random process, then it has a power spectrum s of x, okay? And you filter it with h of mn, which is the point spread function, and then the power spectrums are related by this expression, okay, where this is the Fourier transform of the impulse response of the filter squared, magnitude squared. So the way of thinking about it is this: if you have x of n, okay, and you put it into a filter, h of n, okay, and you get an output y of n, right? Now, this thing has a power spectrum. So you know that by linear time invariant filter theory, you can just take the Fourier transform of this. It becomes h of e to the j omega. You put it into the Fourier transform of this is h of e to the j omega, right? And that the output y of e to the j omega is equal to x of e to the j omega times h of e to the j omega, right? This is just the basic result of linear time invariant filter theory, okay? Well, what this says is that the power spectrum if this is s of x of e to the j omega, that's the power spectrum of x, then the output power spectrum sy of e to the j omega is going to be equal to sx of e to the j omega times, you might think it would be 8 e to the j omega, but it can't be that. Excuse me, because the power spectrum has to be positive. I mean, it has to be non-negative, non-complex. It can't be complex, right? It's got to be real value. It's energy. Okay? So you multiply this by the Fourier. So if this were this can be complex. The Fourier transform of the impulse response. This is the transfer function. So you multiply it by its magnitude squared, and that's the relationship. Okay? It's very intuitive. So the result is that you can compute the output power spectrum by taking the input power spectrum times the frequency response squared, magnitude squared, and then if you take the inverse Fourier transform of that, that means that you take the autocorrelation of the process x, and then you convolve it with h in its time reverse or its space reverse, and you get the autocorrelation of y. And this is how you calculate the power spectrum of most random processes. This is probably the most common mechanism for calculating the power spectrum of a random process. Now, this is there's a theorem then that shows that this is true, and it's called the Wiener-Kinston theorem. But anyway, you can use this basically as a mechanism for generating random processes with any particular power spectrum you want. So you can start off with a random process where the samples of the random process are, say, Gaussian and independent identically distributed. They don't even have to be Gaussian. All they have to be is second order, but let's say they're Gaussian. So there's 0 mean and variance 1, okay? So you can do this in MATLAB, because in MATLAB you can just call the random number generator, the pseudo-random number generator, multiple times, and you'll get independent samples. So this could be in time or space, but actually it's a little easier to explain in time, okay? But it's the same thing in space. And so you just get independent samples of x, and now you pass it through a linear time invariant filter, and you can produce any power spectrum you want, because the autocorrelation, if the random process samples are independent, then they're uncorrelated. So the autocorrelation function for this random process is just a delta. Now, the power spectrum then is the Fourier transform of the autocorrelation, and the Fourier transform of the autocorrelation of a delta is 1. So this is what is often called white noise. And the reason it's called white noise is that we'll see later that white light white light, roughly speaking, is uniformly distributed in power spectrum, okay? That statement is not really true, okay? But it's kind of roughly, approximately, sort of true, okay? As an analogy to white light, they call it white noise, okay? Because the power spectrum is uniform. So you can generate very easily in MATLAB noise with a power spectrum of 1. So then you put it through any filter you want, and then the associated power spectrum of the signal that comes out of the filtered signal is actually got the power spectrum, which is 1 times the power spectrum of the filter squared, the magnitude of the filter squared, right? Now, this is one of my favorite topics, I have to honestly tell you, prediction, okay? I love prediction, okay? Prediction is so fundamental to everything. It's the universal truth, the answer to all questions. No, not really, but anyway, it's pretty good, okay? So prediction. Why is prediction so important? Because if you can predict something, then you can model it. Okay? If you can think about it, this is actually true in just ordinary human behavior. If you feel like you have a good model for a person, a place, a thing, a nuclear power plant, then you can predict what the person, place, or thing or nuclear power plant is going to do. Okay? Now, you may not be able to predict deterministically what it's going to be able to do, but you should be able to give the probability distribution of what the outcomes are going to be. Okay? And this is why probability is so important, because in real systems, you can usually not exactly know what's going to happen. Okay? But you should be able to say, well, the following range of things might happen. Okay? So prediction is very fundamental, and let's say you have a zero mean, without loss of generality. Let's always assume that I'm talking about zero mean Gaussian random processes, and we'll say it's wide sense stationary. Okay, and so y of s is a Gaussian random process, which means that any linear combination of the samples is Gaussian. And it's zero mean and wide sense stationary. I have 2D here, and all my notes are for 2D, and that's fine. But I'm going to give 1D examples, because it's easier to think about. It's all the same. Okay? And then you use the past samples. So a y subscript less than s is the set of all samples before time s. Okay? And now we say, okay, y hat of s. Hat there implies that it's a estimate of y of s. So y hat of s is a random variable. It's a random variable because it's a conditional expectation. And if you recall, conditional expectation is a random variable. So it's a random variable, which is the conditional expectation of y of s given all the previous values of y. So this is an optimal predictor, okay? Because it's minimum mean square error. It turns out the conditional expectation minimizes the mean square error of your prediction, okay? So the difference between y sub s and y hat sub s is x sub s is the prediction error. The prediction error is that. Okay, now there's some very interesting things that are true. Okay, what's amazing is with just these few assumptions. I mean, we didn't really make any serious assumptions about the underlying. Well, we said it was Gaussian, but it's going to actually turn out it could be any really second-order wide sense stationary random process. It doesn't actually have to be Gaussian. Okay, but it turns out that the following is amazingly true. If you look at the correlation between xs, x is, remember, the prediction error. If you look at the correlation between xs and xr for s and r not equal, okay, then the expectation of x, and this is zero mean, remember. So the correlation between xs and xr is 0. So prediction errors are uncorrelated. And it's just a property of the fact that they are prediction errors. They're minimum mean square error prediction errors. And the reason, one way of thinking about it intuitively is that it's because if there was information in one prediction error about the other, then you could have used that to do a better job of predicting. But this is the formal proof, okay? You can go through it line by line. Now, if it's a Whiteson stationary random process, furthermore, the prediction error's variance will not be a function of time, s. Because if it were a function of time, then it wouldn't be stationary. By definition, stationary means the statistics of the random process don't vary with time. So this must be a constant. So now what you have is you have that the prediction errors are uncorrelated with variance sigma squared. So, and remember, and the other thing we know is that because this is a Gaussian random process, that the minimum mean square error linear predictor is a linear function of the previous y's. Now, it also might have a constant, except for we assumed that everything was zero mean. So since everything's zero mean, the constant must be zero. So the minimum mean square error linear predictor is a filter like this that isn't a function of time. So it's got to be a linear time invariant filter. So this is an LTI filter. So what we've got is this. We've got that the input here is y of n, okay? Now we want to compute the optimal predictor. So the optimal predictor is a linear time invariant filter, which is not a function of time. So we convolve with h of n. There's some filter which is going to give us the optimal output, and this is going to be y hat of n, right? And then we take y hat of n and we subtract it from y of n, so this is minus plus, and the result is x of n. So from this we know that, now by the way, x of n is IID, right? So r sub x of n, they're uncorrelated. We proved that the prediction errors have to be uncorrelated. So since they've got to be uncorrelated, it's got to be a delta function because it's only correlated xn and x, say, the expected value of xn and xm equals 0 for n not equal to m. We proved that. And for n equal m, well, it's got to be something. We just say it's sigma squared. Whatever it is, it can't be a function of n and m, so it's a constant. It's sigma squared. So this thing here is going to be sigma squared. So from here we see that the power spectrum Sx of e to the j omega, this is sigma squared, because the Fourier transform of a delta function is 1. See, this is the Fourier transform of this. These are Fourier transform pairs, right? And the Fourier transform of a delta function is 1, and this is times sigma squared, so it's just sigma squared. So this is white noise with variance sigma square. And then from here we can work backwards. We know what we can calculate the transfer function of this filter. It's going to be 1 minus h of e to the j omega, right? Because this is 1, and this is minus h of e to the j omega. So we take that thing, and we square it, and that times s of y of e to the j omega has got to be equal to sigma squared. Because the power spectrum of x is sigma squared. So if we solve for this, we get that sy of e to the j omega equals sigma squared over 1 minus h of e to the j omega magnitude squared. Did everybody follow that? That went kind of fast, maybe. So let me just review it. A prediction, this is an optimal prediction filter. If this is a zero mean Gaussian stationary second order random process, then the optimal predictor has got to be a linear time invariant filter. It's got to be time invariant because the whole thing is the random process is stationary. So the optimal filter can't be a function of time. Okay? And it's got to be linear because it's a Gaussian random process. So after you subtract off this optimal prediction, What's left over is the prediction errors that we proved are independent, uncorrelated. And they have some variance. Whatever that variance is, we just define it as sigma squared. So this power spectrum here is just sigma squared. But furthermore, we know that this power spectrum has to be that power spectrum times this filter response squared. That filter response is 1 minus h of e to the j omega squared, then, okay, times s of y is sigma squared. So we solve for this, and we get that s of y, the power spectrum of this y, must have been sigma squared over 1 minus h of e to the j omega, okay? We say that, okay, now, this is the deal. Okay, so this is true for any second order stationary random process. Actually, it's true for any second order stationary random process, but we assumed Gaussian here. Gaussian means that you can get a little more strong results, but this is really true for any random process. But let's say Gaussian, okay? So you have any Gaussian stationary second order random process, you take its, the power spectrum can be represented this way, where H here is the optimal prediction filter. Now, there's one special case which is kind of interesting, and it's really more of a technicality, but it's sort of an important technicality, which is that there's two possibilities. H here could be an infinite impulse response filter. In other words, it could use all the past values of y to calculate the optimal prediction. And in the general case, that's what would happen, right? I mean, you would need all the previous information. But you can assume under some conditions, and it's often a very reasonable modeling assumption, that you only need a finite amount of past data. If h of n is FIR, then we say that y of n is an AR random process. See, it's not, this isn't a very, this is true for any stationary random process. So if you allowed h to take on any value, then it wouldn't be a constraint. This would be any stationary random process. But if you assume that this has to be FIR, has to have a finite number of previous samples, then we say that y is AR. So in practice, as an engineer, if you, let's say that h here, is going to always decay away as n gets large. So let's say you take the first 100 terms, okay? Well, gee, with 100 past values, you're probably going to get a pretty good estimate of the prediction, and okay, so everything, any random process can be approximated by an AR random process to some degree of accuracy. So AR processes are really quite general. The only thing is that, as a practical matter, if the number of terms you have to retain is like 7,000, at some point the number of parameters is like an unwieldy model, right? It's not very elegant. It may not be the right way to go at your problem, but you can basically model any signal, stationary random process that's Gaussian, as an AR random process, okay? Okay, so, right. Now you might ask to say, okay, now, how do I actually generate? So how to generate? Can we zoom out just a little bit on this slide here? Can we zoom? Yeah, that's good. Just zoom in a little. Okay, yeah, that's good. So I can center. Okay, here. So how to generate an AR process. You see, I'll put a question mark here. I haven't told you how to generate it, because here I assumed I had it, and from that I found out what its parameters were. The parameters of the AR process are the H's, the prediction filter, and sigma, the prediction variance. Okay, so we say AR parameters they're sigma squared and what am I doing here? H of n. So that pair, those parameterize the random process. Now, once I have this, how do I actually generate the random process? Well, there's a very clever thing you can do. What you can do is take this filter and invert it. The inverse of this FIR filter is assuming that H has, if it's AR, H is FIR, right? So the inverse of this is an IR filter. So it works like this. You take X of n here, and this is Y of n, and this is H of n, and this is like this, okay? So these are IID. And there's one other thing we want to do. Put a multiplier here and just multiply by sigma squared, right? So these are IID n0, 1 random variables. You scale them up by sigma, not by sigma squared, by sigma, okay? You multiply them by sigma. After you multiply the n0, 1 random variables by sigma, then they're n0 sigma squared random variables. And then you pass them through this filter here. And what you get out is AR. This is AR random process. So the AR random processes are kind of useful because you can generate them in a computer very easily. And you can actually, if I give you a signal, say like a speech signal, and you want to find the parameters of an AR random process, well, how do you do that? Well, you find an optimal predictor. So you find the best predictor. Now, you've done the image restoration lab so far or not? Yeah. Okay. How many, has that been due yet? Is the image restoration? Okay. So you guys so we're synced up perfectly now. It only took half a semester to get here. Okay. So this filter could be the optimal predictor that in your lab, you had to design an optimal predictor, right? So you find the optimal predictor for predicting the current value of y from the previous values of y, and now that becomes the parameters of a model. Then you also estimate what the variance of the remaining prediction error is, and from that you have you have AR parameter models, and now you can generate a sample from that same random process. Now, if you take something like a speech signal, right, and you estimated those parameters and generated the signal, well, there's a question of whether that signal you generated would really be like the original signal, okay? If you just took something like speech, you took 5 minutes of speech, you estimated the AR parameters, and you played it back, it would just sound like noise, right? So it wouldn't be much like a speech. But if you take very small segments of speech, you can model this pretty accurately. But the problem is speech is not stationary over long periods of time. But it is stationary over very short periods of time. And that's what an LPC coder, a linear prediction coder, does. It actually, rather than transmitting the actual signal, it translates the parameters and it resynthesizes the speech signal at the other end. That's, I think, actually how some cell phone communication works. And it's really it's like dehydrating food and then reconstituting it on the other side, It's not quite the same thing, but, it tastes good enough. Okay. I think I'm going to skip the rest of this because I just talked about it. So these are just the formal notes that explain what I just explained, okay? Now, what you can also then is you can use this as a method of doing spectral estimation because, remember, we had a formula here for the power spectrum of Y. So if you estimate the prediction filter coefficients, this gives you a way of estimating the power spectrum. And this estimate of the power spectrum is more accurate, or can be more accurate than the one that we did in the lab. It has a better Biasvariance tradeoff. But it's because it's based on a model, which is your model is that the signal is an AR random process. Now, this is the beauty of models, okay? Models are wonderful if your model is correct. And models are terrible if your model is incorrect, okay? or at least they can be terrible. Okay, so it's as the story goes with the old what's his name? The guy. What's the guy's name? I got to remember his name now. The guy who was mayor of Carmel, California. The good, the bad, and the ugly. What's the guy's name? The movie star. Clint Eastwood. Thank you. Okay, it's like the good old Clint Eastwood thing: the good, the bad, and the ugly. Okay, so you have to take the good and the bad together. So the important thing is that you guys are the keepers of the power tools without the blade guards. Okay, so you have these high power tools. You have to know how to use them. Okay, so used correctly, they can be very effective. Used incorrectly, they can work very badly. Okay, they have to be used judiciously. You have to understand what the underlying assumptions are. And I talked about this, generating AR processes. So I want to get on to the next topic, trying to catch up a little bit, which is actually the topic of the previous lab, I believe. Is that correct? Which is multivariate Gaussian distributions. These come up a lot. So if you have a random process, very often you have x, you have x, okay, and x is a vector. So it's x1 through x, what's the dimensionality I'm using here? I think I used the letter P. XP. Okay? So this is a member of R to the P. It's a random process. Okay? Or it's a random vector. Okay? And so let's say it's Gaussian. So we say that X is distributed as n mu R, okay, where this is R here, this is the mean, and this is covariance. And R has the following property. R is symmetric. Are there two M's in symmetric? I don't know. And positive definite. Does everybody know what positive definite means? Positive definite means that for all x, a member of R to the P, x transpose Rx is greater than 0. Okay. And so R has to be positive definite for this to be a valid definition. And then the density function, P of x, for this x, if it's a multivariate Gaussian, is equal to 1 over 2 pi to the P over 2 times the exponential of 1/2, I see there's an error in my notes actually, x transpose R inverse x minus, okay? This is just like the 1/2 that you have in a Gaussian density, and R inverse here plays the role of 1 over sigma squared. So R is like sigma squared in the case of the one when p equals 1, right? And then we also have to normalize this, so this becomes R determinant to the minus 1/2, okay? So that's a multivariate Gaussian distribution. It comes up a lot. And, Gaussian distributions, to me, are analogous to linear time invariant systems. Most real systems are not time invariant, and maybe they're not linear, okay? But linear time invariant systems are a great baseline to construct more complicated models. So from linear time invariant systems, you can adapt those models to describe things that are not linear and not time invariant, right, or time varying, right? And Gaussian models, multivariate Gaussian models are the same way. They're very powerful concepts because they can be applied to model things that are non-Gaussian and more complex, okay? But they're sort of the first step, okay? So understanding these is very powerful. So that's what that lab was about. And we'll talk about this in the next lecture. So good seeing you again. Thanks. Bye.